we're going to go over the process for using a computational environment in order to generate random values. So as you move throughout the remainder of your engineering coursework, you're often going to be asked to model or understand situations that involve some type of uncertainty. And the mathematical tool that you will utilize in order to do that is the concept of random variables. And if you're going in the electrical and computer engineering route, you're actually going to take an entire class on the idea of random variables and probability distribution functions and whatnot, and just understanding how to deal with this type of mathematical tool. So clearly, we only have about 5 minutes to talk about them, so they might still be a little bit confusing after we're done, but hopefully you'll get the basic idea of why they're useful with respect to describing situations with some type of uncertainty. So random variables, what they really are is a function. So if you have some outcome that is uncertain, I should say some experiment, where the variety of outcomes could occur, and which particular outcome will occur has some uncertainty associated with it. A random variable is just a mathematical tool to take those discrete outcomes that happen in the real world and kind of make them tractable and put mathematics behind them. So if you flip a coin, naturally, if you were to flip a coin in front of you, physically two things could happen. You could have a heads appear, or you could have a tails appear. If you were to roll a dice, 6 things could happen. You could have the value 1, 2, 3, all the way up to 6 happen. If you were to take a measurement of a voltage across a resistor and you didn't have any voltage connected to it, you would measure a little bit of voltage associated with just some random process, which is known as thermal noise. And that value would be continuous. It could actually be anything in the world. So all that random variables are is they take these situations that have a variety of uncertain outcomes that could be countable, which are known as discrete. In the case of the coin flip, you had 2 outcomes. In the case of the die roll, you had 6. Or they can be continuous. They can take on any value within a range. That would be like the case of the noise measurement that we spoke of. And random variables just take those actual outcomes and they map them to typically some type of number. So in the case of actually flipping a coin, you could call the head 1 and you could call the tails -1. In the case of actually measuring those random voltages that could show up across the resistor, the most natural thing to do would be to actually just take the values that you measure and use those as your kind of quantitative or measurable numerical outcomes. So the random variable just takes and maps the uncertain outcomes in the real world and puts a number behind them. And once you have a number behind them, you can actually assign an idea of a probability. And a probability is just a measure of how likely each of those outcomes is to occur. So in the case of the coin flip, you could have a head or a tail, and you might use a random variable to map those two outcomes to a 1 or a -1. And we might reasonably assign a probability of 1 and -1, to 1 and -1, I should say, of 0.5, indicating that both are equally likely to happen. And since both are equally likely to happen, the reason that I chose 0.5 is the sum of all possible outcomes we would want to be 1, indicating that 100% of the time, one of those two outcomes would happen. In a similar fashion, when we're rolling the die, if we wanted to kind of mimic the case of an equally likely outcome, we wouldn't use a probability of 1/2 as an assignment. We would use a probability of 1/6, such that if we sum the probability of the associated values of the random variable, it would add up to 1. That's in the case of a discrete random variable. We could assign some what's known as mass of probability to each of the possible outcomes. In the case of a continuous random variable, we don't assign a mass, we assign what is known as a density. And the density is supposed to be some kind of reasonable measure of how likely a particular outcome is to occur. So if we have a discrete random variable, that probability distribution function will be discrete. It's known as a mass function. If we have a continuous random variable, it will be a continuous function, and we call it a density function. And here are 2 of the common ones that we're going to look at throughout the remainder of this learning module. On the left, we have a discrete probability mass function. And if you notice, each of these outcomes, 1, 2, 3, 4, 5, and 6, I've assigned the same probability to it. So I would call this a discrete uniform probability distribution. So this would correspond to something that has 6 outcomes, all of which are equally likely. If there are only 2 outcomes, I would have just 2 dots here. Each would be a half. But in both cases, a uniform probability distribution function, or a mass function in this case, all of the probabilities would sum to 1. On the right, we have a very familiar probability density function, because if you notice, the values of the random variable that it can take on are continuous, and this is known as a Gaussian or a normal distribution. And right there in the middle of what appears to be a bell curve is our mean value, and if you notice, the mean value here is 0. And if I were to take some measure of how thick the curve is around its mean value, that would be related to what's known as the standard deviation of this Gaussian curve. So this is a particular type of normal or Gaussian distribution. It is a unit or a standardized normal distribution. And standardized normal distributions have a mean of 0 and a standard deviation of 1. So just kind of keep that in mind. Normal or Gaussian distributions look like the bell curve. They're continuous. And discrete distributions that are uniform are going to just have a bunch of dots for each outcome, and each dot will be the same height. And if you add them, it will sum to 1. For the continuous case, we would need to integrate in order to find that integral over the entire range of possible values is 1. And one more thing I should say, if you want to find the probability of any particular value, you actually can't. If you were to evaluate the function in a particular value, that value would be the density. If you want to estimate the probability of that value, you need to integrate some very small range around that value, and that integral would give you the probability of the actual outcome being in that range. So let's talk about how you generate random numbers in computing. Well, the first thing you should know is there are a ton of different applications where you're going to be required to do this, especially if you're working in emerging applications like artificial intelligence. They highly rely on the generation of random numbers in order to split data into testing and training sets in an unbiased way. But that's not the only thing. You could just be building simulations of outcomes that are uncertain. That's kind of what we're going to do in the example within this learning module. One thing you should know is if you're working with a computer, it's never going to be able to generate purely random values. If you generate a sequence of enough of them, if you did 10,000 or 100,000, or depending upon the quality of the random number generator, eventually you would start to see a little bit of the pattern. And that's why computer-based random number generators are known as pseudo-random. However, the ideal is that the pattern of repetition is so long that for our practical purposes, we can just consider them random. So when you're generating a pseudo-random number on a computer, you can kind of choose the process to mimic the data that would be generated by sampling from an underlying probability distribution function. And I'll actually show you what I mean by that in the next few slides. So within MATLAB, there's 4 functions that you need to be familiar with. The first is rand. And what rand is going to do is return a continuous random number between 0 and 1 that's drawn from a uniform probability distribution. So let's just type it in and see what happens. If you type in rand a bunch of times, what do you notice? Well, the first thing you notice is every time the value is changing. And every time the value is between 0 and 1. And ideally, if we generated enough of these, we would find that the likelihood that a small value, like near 0, would be generated is the same as the likelihood that a larger value, near 1, would be generated. So the question is, how do I actually generate a bunch? Well, for all these, you want to go to the help files, and you'll notice that this is an overloaded function. There's multiple ways to call it. You can call it by passing in a single parameter. In that case, you will get an n by n matrix of random numbers. So let me just show you that. If you type rand3, you'll get a 3 by 3 matrix. Or if you go back up to your help file, you can actually pass in an array where you specify the number of rows and the number of columns. So if I do something like rand 110, I would expect to get a row vector or a row array with 10 elements. And if we just look at this, does it look like it's uniformly distributed between 1 and 10? Well, all the values are between 1 and 10. We got a couple near 3.3 something. That's not very likely. The only way we could really probably quantify it, though, is to take those values that we're generating and draw a histogram. Because if we drew a histogram, which is kind of, you can think of it as like a statistical approximation based upon data of the probability distribution function, this histogram should look pretty uniform or pretty flat. And if you notice, in this case, it doesn't. If I generated 10 data points, in this case, 8 are between 0 and 0.5, and only 2 are between 0.5 and 1. So let's close it and try it again, because remember, every time this executes, it's going to generate 10 new random values. Well, that's a little bit better. 4 and 6. In general, I'd expect 5 and 5. 3 and 7, not as good, and so on and so forth. Here's 5 and 5, perfect. But what we're actually seeing is what's known as sampling effect. When we only generate a small number of random values sampling from an underlying distribution, it's not very likely that the data that we get will perfectly resemble the nature of the underlying distribution. Usually, in order to make that happen, we have to generate very large data sets. So rather than generating 10, let me generate 100, and let me do that a bunch of different times. And you notice in the case of the 100, I don't get those really, really asymmetrical distributions that I did when I only generated 10. They're not perfect, but again, they look much more uniform. If I did 1,000, I should notice that will become even more prevalent. And part of what we're seeing is a little bit of a distortion here because the bin widths are changing. If you notice in the case of 10, it bin from 0 to 0.5 and 0.5 to 1. Here the bins are much more granular. They're 1/10 wide. But if you eventually make this big enough, what you should find is that the sample of data you get actually looks like something that was drawn from a uniform distribution. So that is the rand function. What if you don't want continuous numbers? What if you want integers? Well, randi is what you would use for that. So let's actually see what randi does. So I'm going to clear this, and I'm going to go help randi. And if you read, you'll notice that it is generating, and a lot of times it's easier just to look at the example code. It generate integer values from the uniform distribution on the set of 1 to 10. Well, let's just run this and see what happens. So let's look at R. If you notice, R is 100 rows by 1 column. It's a column vector. And if I were to look at a histogram of R, we notice that it has a bunch of values between 1 and 10. The histogram is not the perfect thing to use here because maybe a better way to do it would just be to plot the values of R. That way we can see them. And again, it's linear interpolating in between. But if you notice, every value that you get is between 1 and 10. And ideally, each of these should be equally likely. So if we were to run that histogram, knowing that if we don't specify the bin size, we're going to see some things that look a little bit distorted because it's going to look like you have a value greater than 10. You don't. It's just the way that it's chosen the bins. But if I were to make the number of samples larger, rather than 100 go to 1,000, I would expect that that histogram would look more and more uniform if I repeated the process a bunch of different times. And that's what's going on. So here in this syntax for randi, you notice the last two values are the kind of dimensions of the random matrix that you generated. And the first argument, 10 here, like if I were to rerun that and make 10.5 instead, what you'll notice is that's kind of the upper bound of the random integers that you're generating. So they go from 1 to whatever that number is. And if you look at the various versions of the overloaded syntax, you'll see you can actually set the lower bound less than 1 if you would like as well. So rand generates uniform random values from 0 to 1. Randi generates random integers on a uniform distribution. You specify the upper bound and the lower bound. Rand_n actually is going to be used in order to simulate values from a standard normal distribution, meaning that it has 0 mean and uniform standard deviation. What this means is that the standard deviation is equal to 1. Just making sure to plot that in there before I forget to add it. So if I use rand_n, notice that I technically could get any value here. And if I look at some different syntaxes of rand_n, you can see that the way that it works is much like the rand function. You specify in the size of the random matrix that you want to generate. So I'm going to generate a 1,000 element row vector here. And if I plot, and I could save it as a variable, but I could just plot the histogram directly, since that's all I want to do is look at how this distribution looks. And it would help if I actually called the right function instead of rand, if I called rand_n. I knew I made a mistake there because rand, remember, it generates according to a uniform distribution, and it kind of just looked like a rectangle. But if I rerun this with rand_n, I get things that look much more like a Gaussian distribution. And if I repeat that a bunch of times, I won't get much variability. If I generate more data points, I'm going to see less of a sampling effect, and I get a much more smooth bell-looking curve. So that is rand_n. The last one you want to know about is rand_perm. That's if you want to generate an array of integers with no repeated values. And just to keep this video kind of short, I'm not going to go through this in this video. I might give you a kind of a homework or a next exam question related to it that would cause you to dig into the syntax. But this is very valuable if you're like importing 500 files and you want to choose which subset of the 500 files is going to be your training or testing data. Random permutations of integers are a really important thing to know. So you can kind of dig into the detail of the syntax of those functions if you're interested. But let's actually do a little bit of an example here. Let's write a MATLAB script to simulate 10 trials of a coin flip. How many head outcomes would you expect within the experiment? How many were present? And then let's repeat the simulation for 1,000 trials and generate a visualization to see what's going on. So the question is, what of the various functions that we talked about would be the most appropriate here? So hopefully you thought it would be randi, because if you remember, randi is generating the random integers. But remember that this is we need to define a random variable, because the outcomes here in the experiment are heads and tails. what I'm going to do is I'm going to call head be equal to 1, and I'm going to call tail to be equal to 2. And I can do this any way I want. I just have to pick two different numbers. But the reason I'm doing that is if you remember, rand I actually puts the upper bound at whatever value you pass in. So if I have rand I 2, if you notice, it's only going to generate either a 1 or 2. And it seems that the majority of the time here, it's generating a 2. But let's actually take in and let's define our number of flips. So I can pass that in as a variable. So I'll say n equals 10. And what I want to do is use rand I, and I will say that I want to generate random values up to 2, and I want to generate a 1 by n array of random values. So that's what this will do. This will generate random values from 1 and 2 uniformly distributed, and it will be an n element row vector. So let's actually do that. And we could save this if we want. I'll call that coin flip. And we can run that. And let's not put a semicolon. That way we can actually see the values that are generated. I'll go to the editor and actually run this. And if you notice, you got 2, 2, 2, 1, 2, 1, 2, 2, 2, 1. So out of these 10 trials, we're calling a 1 a head. So this is 3 heads and 7 tails. If we do that again, if you notice in this case, we got 1, 2, 3, 4, 5 heads. 5 heads and 5 tails. That's kind of what we would expect. But because of the small numbers of samples that we have, if we run this a bunch of times, that case of getting 5 and 5 isn't going to happen very often. So that's kind of the first answer to that question. If we run this only 10 times, we're not going to get that 5 and 5 outcome that we would expect very often. However, if we take this up and we make it 1,000 trials and we rerun it, and instead of actually just looking at the actual values that are produced, if we do a histogram, so I could call these my trials, I could assign these random values to a variable called trials, and I could pass that random vector into a histogram. I'll suppress the output since I'm going to be spitting out 1,000 numbers now, and I don't necessarily want to see that. If I rerun this code, notice if I run it 1,000 times, for the case that I ran it, I got 501 heads and 499 tails. And if I repeat that, this time I got 487 and 513. But the key point is when you have a larger number of samples, you're not going to get those kind of sample level outlier effects where the data is very disproportionate, where you have a few number of heads and a large number of tails. As long as you don't have those sampling effects, you're repeating the trial large enough, you're going to see relatively uniform data as you would expect since you're drawing from a uniform distribution. So hopefully that was helpful. I'm sure it was a little bit confusing because we really went over a lot in less than 20 minutes, but you'll get an opportunity to kind of play with this as part of your homework this week.